So in this video, we're going to be looking at how to calculate the distance between 2 points. And in general, we have the distance formula. We're going to look at this in 2 dimensions, although this generalizes to 3 dimensions if we need it to. So essentially, we're just looking at the rectangular coordinate system version of the Pythagorean theorem. We have the difference in our 2 x's squared, that's one side of our right triangle, difference in our 2 y's squared, that's the other side of our right triangle. And so the straight line distance between them is the length of the hypotenuse. So we add these up and we take the square root of the sum. So let's consider some examples. Find the distance between the points to 4 and -3, 1. Okay, great. So now our distance. So the 2x coordinates, now because we're squaring it, it doesn't matter which order you subtract in. You don't even need to be terribly consistent about it for this to work. But it's good to be consistent in other cases. So 2 minus a -3 squared and 4 minus 1 squared. So 2 minus a -3 is 5 squared, and 4 minus 1 is 3 squared. And so we're going to end up with 25 plus 9, which is going to be the square root of 34. And again, expect square roots unless the problem is chosen extremely carefully. You're going to end up with square roots. Now let's take this up into 3 dimensions. Find the distance between the points 1, 5, -2 and 3, 8, 6. Now for this, we're going to extend our distance formula to 3 dimensions. And so underneath the radical, we're going to have a pair of z coordinates as well. So if you're trying to find, for instance, the diameter of a sphere, you might need to do this. But it basically generalizes. So our distance formula in this particular example, again, order of subtraction doesn't really matter because we're going to square things, so that'll take care of any sign differences. Again, it's a good idea to be consistent even when it doesn't matter because it will in other cases. So 1 minus 3, and then in our y coordinate, 5 minus 8, and then in our z coordinate, -2, -6. And this is going to give me -2 squared and -3 squared, and then -8 squared. None of the minuses are going to survive the square. That's important. You should not be subtracting under the square root. You should end up adding everything. So -2 squared is the same as 2 squared, which is 4. -3 squared, same as 3 squared, which is 9. And 8 squared is 64. And that's going to give me 4 plus 9 plus 64 is 77. Now, you can also use the distance formula to come up with an equation for the distance between a function and a point. Find the equation that represents the distance between a point, let's say 2, 5, and the function y equals x squared minus 1. Now think about the point on the curve being xy. And so the distance between the point xy and 2, 5 is going to be 2 minus x squared, or you can subtract in the other direction, and 5 minus y squared. But we want it just in terms of one variable since y is written in terms of x. And so we're going to replace y with x squared minus 1 plus 5 minus x squared minus 1. And let's see if we can simplify this a little bit. Two minus x squared, we're going to FOIL that out in a second. 5 minus x plus 1 is going to give me 6 minus x squared. And so 2 minus x quantity squared is 4 minus 4x plus x squared. And 6 minus x squared is going to give me 36 minus 12x squared plus x to the 4th. And if I combine like terms, I get x to the 4th minus 11x squared minus 4x plus 40. And so now this represents a formula. If I have some point on the graph of y equals x squared minus 1, I can plug that into this equation, and that will tell me how far that point on the curve is from the point 2, 5 at any point along the curve. And so I can also use this, for instance, to find things like the minimum distance or the maximum distance if there is one. And I can, for instance, plot this curve and plot this equation, and it will give me lots of information about the changing relationship between points on this function and points on this particular point.